In section 4.4, I'm going to do some numerical examples of projectile motion problems. There's a few main strategies to keep in mind when doing projectile motion problems. And the first is that we have to keep the x and the y directions separate. We're going to set up a givens and unknown table where we have a column for the horizontal or x motion variables. We're going to set up another column where we have the vertical or y direction variables, and we're going to keep those two columns as separate things. The second thing is to remember that objects in projectile motion are also in free fall, and so we know what the acceleration is. We know that the acceleration has a value of g, and it has a direction of downwards. And when we're keeping the two directions as separate, we now have to use the components for the acceleration. And so the acceleration in the x has to be 0, and the acceleration in the y is g. And usually we like to make up our positive direction, which would make down our negative direction. So we would have to use a negative sign to indicate that the acceleration of an object in free fall is down in the negative direction. And as a reminder, g has a value of 10 meters per second squared that we would use on positive physics. And g in the real world has a value of approximately 9.8 meters per second squared. The third thing to remember is that objects in projectile motion have a uniformly accelerated motion, or UAM. And so the UAM equations that we learned from the last two chapters are still going to be relevant, and we can still use them, but we have to remember that we're keeping the x and y directions separate, and so these equations can be applied twice, once to the x and once to the y. All right, let's look at an example. Here we have a rock that's thrown horizontally from a 20-meter high bridge with a speed of 10 meters per second. And we want to calculate its time of flight, its horizontal distance traveled, and the rock's speed when it lands. So we should pick out the important information that's given and the requested values to be calculated. I'll highlight them here. And we would like to organize this in a givens and unknown table. And when we do this, we have to make a column for the horizontal motion and another column for the vertical motion, because we have to keep the x and y directions separate. So the variables that we can possibly find, it helps to list out. And I'm going to do this on both sides, both columns, the same information. The values that are vectors, which include delta x and delta y, the initial final velocities and accelerations, all need to be separated into its x and y components. So I'm going to add x and y subscripts to all the values that are vector quantities. I don't have to do that with t because t is a scalar quantity. It does not have direction associated with it. Okay, so what do we know? Well, we know that the rock is thrown horizontally from a 20-meter high bridge. So that means that its y position from where it starts to where it ends is going to move downwards. So that's why I'm going to give a negative sign to delta y. It moves downwards 20 meters. I don't know its change in horizontal position. That's what's asked for in part B of the problem. As for the initial velocity is 10 meters per second, and it has a direction of horizontal. So this is what the initial velocity looks like. And if I was going to separate this out into components, there's no way for me to draw a y component. That's because there is no y component to the initial velocity. The initial y component to the velocity is 0. And that's because all of the initial velocity is in the x direction, and so the initial velocity is the x component. The x component to the initial velocity is 10 meters per second. The vertical component is 0. We'll skip the final velocity for now, and we'll move on to acceleration. The rock is going to be in free fall, so we know its horizontal acceleration is 0, and we know its vertical acceleration is negative g, and we're going to use a value of 10 for g, meters per second squared. We don't know what the time of flight is. That's requested in part A. And for the final velocity, we can actually fill in v final in the x direction because there is no acceleration in the x. That tells you that the velocity in that direction is a constant value. So the final and initial velocities in the x direction are the same value. I don't know what the final velocity in the y is, and I'm going to need to solve that because that's going to contribute to the rock's speed when landing. So I'm going to need to figure that out for part C. Okay, so starting with part A, I need to now choose an equation that can solve for the time of flight with the given information. And here's our list of UAM equations that we have to choose from. Okay, so the equation that I'm going to use, the only equation that has all the information that's given in the problem is this first equation. And I need to use that first equation, but I need to change it up just a little bit. Instead of delta x, I'm going to use delta y. And that's because I know the change in the y position, I know the initial velocity in the y, and I know the acceleration in the y. So I can use that equation, but the initial velocity and the acceleration have to get that y subscript to specify that I'm talking about the y motion. And I know everything in here except for time, so I can fill in. Delta y is negative 20. The initial velocity is 0, so that whole term is 0. The acceleration in the y is negative 10. And now the rest of this is just algebra. Simplifying the right-hand side of the equation, half times negative 10 is negative 5. If I divide both sides by negative 5, that gets me t squared. And so that is equal to 4. Well, if I have to take the square root to find t, t is going to be 2 seconds. So now I know what the time is, and I can use that later on to solve for part B. Okay, so now for part B of this problem, where we have to calculate the horizontal distance traveled. So that is going to be delta x. Now that we know the time, there's a few equations that we could use. We could use this one, and that's the one I'm going to use. Alternatively, we could also use this one or this one. So I'm going to use this first one to solve for the horizontal distance. Delta x is v initial, and I have to put an x subscript to specify that I'm talking about the horizontal velocity, plus 1/2 a. Again, I have to put a subscript x to specify that I'm talking about the horizontal acceleration. And now I can fill in with the values shown in my table, plus the time that I found that was 2 seconds from part A. The initial x velocity is 10 meters per second. I'm going to multiply that by 2 seconds. The x acceleration is 0, so that whole term is 0. And we found that the horizontal distance traveled is 20 meters. For part C of the problem, we want to find the rock's speed when it lands. So it helps to picture what the rock is doing when it lands. The rock is still moving horizontally, but now it's gained some y velocity. It's moving downwards when it lands. These components can be labeled Vfx for the final velocity in the x direction and Vfy for the final velocity in the y direction. And the overall final velocity looks something like this. And the magnitude of that final velocity is going to be our speed. This is what we are looking for. We're looking for the magnitude of the final velocity. So, as mentioned before, the velocity in the x direction is constant, so we know what that final x velocity is. It's the same as the initial x velocity, 10 meters per second. For the final y velocity, we're going to need to find that. So, we can choose any of the equations with v final in them. This is the equation that I'm going to use. Alternatively, we could use this one, or this one. But the simplest one to find is this second equation, so I'm going to use that one. Again, I'm going to have to specify that we're using the components of the velocity and acceleration vectors. The initial y velocity is 0. The acceleration in the y is -10. And in part A, we found the time of flight was 2 seconds. So that means the final y velocity is -20 meters per second. And that negative sign is indicating that it is moving downwards at 2 seconds. Now that we have the two components of the rock's velocity when it lands, we can then find the magnitude of its velocity. These components make up the legs of this right triangle, and so we can use the Pythagorean theorem, right? Leg squared plus leg squared is hypotenuse squared. We know the values of the legs, and so we can now calculate the hypotenuse. 10 squared is 100. 20 squared is 400. So we want to know what squared is 500. So the magnitude is going to be the square root of 500, which is 22.4 meters per second. That is the final velocity, which is the final speed. Okay, let's look at one more example. Here we have a baseball that's hit with a speed of 50 meters per second at an angle of 37 above the horizontal. The ball is going to land on the ground. We are to neglect drag and the initial height of the baseball. We assume that the field is flat, and we need to calculate the time of flight and the horizontal distance traveled. Again, we'll pick out the given information and the requested calculations to be made, and we're going to organize that in a givens and unknown table. Again, I like to start out by listing all of the variables that we could possibly find, and I'm going to have to make the same list again on both sides. That's because we have to treat the x and the y directions as separate things. Again, all the vector quantities, displacement, initial final velocity, and acceleration, all need to have x and y subscripts so that we can specify that that we're only talking about the x or the y part of those vectors. And again, t does not need subscripts because t is not a vector, it is a scalar. It does not have a direction. Okay, so the speed of the ball is 50 meters per second, and it's launched at an angle of 37 above the horizontal. So we're going to need to figure out the components of the initial velocity so that we can write into our givens table the values for Vix and Viy. The initial velocity has a magnitude of 50 meters per second. The initial angle is given as 37 degrees, and we're going to need to calculate the x and the y components. To find the x component of a vector, I multiply the vector's magnitude times the cosine of the angle with the x-axis. So my x component to the initial velocity is going to work out to be 40 meters per second. That's a rounded value. The y component to the initial velocity can be found by taking the initial speed and multiplying that by the sine of the angle with the x. And again, as a rounded value, here we'll get 30 meters per second. And I'll just complete my right triangle. Again, the shortcut that I used here and here, you can skip those if you just remember that we have a right triangle, and you can use right triangle trig to work out those values. I'll add them to my data table. Okay, so the ball is landing on the ground and the field is flat. That means that from the initial spot to the final spot, there is no change in the y position, right? The initial and final y positions are the same, so overall there is no change in the y position. The acceleration is known. We know that it's in free fall, so we know the acceleration in the y is negative g, or we'll use a value of negative 10, and we know the horizontal or x acceleration is 0. Because there's no acceleration in the x, we know velocity in the x is a constant value. And so the final x velocity is the same as the initial x velocity. For the y velocity, this is a special step that we can make because we know that the y position doesn't change overall. And so just like with one-dimensional motion, when an object returns to its original height, it has the same speed, except it's going to be moving downwards. So same initial and final vertical speeds, just opposite signs. Part A wants us to calculate the time, so that's our unknown for part A. And part B wants to know the horizontal distance traveled. Well, the horizontal distance is the change in the horizontal position. So that's what we're calculating in part B. Okay, so again, we're the object is in uniformly accelerated motion, so we can apply our uniformly accelerated motion equations, and we're going to need to find an equation where that we can use to find the time. Now, really, there's a few ones that we could do because we know all of the information in the y direction except for the time. The one that I'm going to use is this first one. So instead of delta x, we have delta y. The initial velocity needs the subscript y to indicate that we're just using the y component of the initial velocity. Same thing for the y acceleration. And now I can fill in what I know. Now, if we were to solve this equation, you should notice that the equation is quadratic in t, but since there is no zero order or constant term, here there's a special way that we can go about solving this. We can divide every term by t. When we make this step dividing every term by t, it simplifies the right-hand side considerably, right? It gets rid of that t there, and then it gets rid of the squared from that term. what we have left over, 0 divided by t is just 0. We have 30 plus a half times negative 10. That gives you negative 5. And now this is pretty straightforward. I can move the 5t over to the other side by adding it. So that gives me 5t is equal to 30. And then I just need to divide both sides by 5, giving you t is 30 divided by 5, which is 6 seconds. So the time of flight for our baseball is 6 seconds. And we're going to use this now as a given value for part B. Okay, for part B of this problem, we want to calculate the horizontal distance traveled. Well, the horizontal distance is the change in the ball's horizontal position. So I'm solving this for delta x. I have a few options that I can use. I think the most straightforward equation to choose is this first one. So delta x is the initial velocity. I have to use the subscript x because I can only use the x part of the initial velocity. Got to keep the x and y directions separate. Again, I have to use the x component for the acceleration. And I can fill in what I know because I know everything in here except for delta x. So delta x will equal the initial x velocity, which we found to be 40 meters per second, times the time of flight, which we calculated to be 6 seconds in part A. And the x acceleration is 0, so this whole term drops out of the equation. 40 times 6 gives you a value of 240 meters. Okay, same scenario as parts A and B. It's the baseball hit with a speed of 50 meters per second at an angle of 37 above the horizontal. But now we're asked questions about the ball's maximum height. So I have highlighted the important information here. And again, we can construct a givens and unknown table. Most of the values are going to be the same. The values that are going to be different are the values that correspond to the ball's final position because that has changed. In parts A and B, the final position was the ground. And in parts C, D, and E here, the ball's final position is the maximum height. The most important thing to remember when dealing with questions about maximum height, max height is where the ball stops moving upwards and starts moving downwards, and therefore it is a turning point in the y direction. The ball's y velocity is 0 at max height. One more thing to keep in mind, though, it is not at rest like when we had one-dimensional motion. The ball is still moving when it's at its max height. It's just not moving in the y direction. So again, we get to apply our UAM equations because the ball has uniformly accelerated motion. And I need to find an equation that solves for delta y, because delta y is going to be the max height. The change in the ball's y position will give us the max height. So the equation that has enough given information to fill in and solve for delta x is this one right here. Again, all the vector quantities, the initial and final velocity, the acceleration, the displacement, they all need to get y subscripts to specify that we're only talking about the y part of those vectors. The final y component is 0. The initial y component to the velocity was 30. The y acceleration is negative g. And delta y is what we're solving for. Simplifying the math a little bit, 0 squared is 0, 30 squared is 900, 2 times negative 10 is negative 20. And we'll have to move the term with our unknown over to the other side to group our unknowns on one side and all the terms without the unknown on the other. And now we can just divide each side by 20, which will give us our answer, 45 meters. All right, for part D, it wants to know the time that it reaches max height. Now that we know what the max height is, there's a couple of, we can actually use any of the equations except the one we just used. The most straightforward one to use is the velocity as a function of time equation. So I'll write that down. Again, all the vector quantities, the final and initial velocities, and the acceleration all need to get the subscript y to indicate that we're only using the y component of those quantities. I can fill in my values. Move the term with the unknown over to the other side by adding a 10t to either side. And then I can divide both sides by 10, which gives me my answer, 3 seconds. Okay, now for part E, the ball's speed and direction of motion at max height. We know what the components of the ball's velocity are at max height. So if I was going to draw that vector out, this is what it would look like. It would just be a sideways arrow with a length of 40 meters per second. That is the speed. There is no y component. All of the velocity is in the x direction at max height. The direction of motion is horizontal. It's moving horizontally. There is no vertical motion at max height.